In the last couple of videos, we talked about how to get the eigenvalues, eigenvectors. We did some examples, and now I just want to finish up with some remarks and some facts about these eigenvalues and eigenvectors that will prove useful in the coming sections. First, let's look at the special case of diagonal and triangular matrices. So diagonal matrix obviously just has non-zero elements down the main diagonal, zeros everywhere else. A triangular matrix is one where the main diagonal is non-zero and all the elements above it or all the elements below it are non-zero and the others are zero. So it's like a triangle of non-zero elements. You talk about upper or right triangular and lower or left triangular. Turns out that in both cases, triangular and diagonal matrices, the eigenvalues are sitting right on the diagonal. So if you think about like a 3 by 3 case and you imagine getting the characteristic equation, you'll quickly realize that the only terms that you get in the characteristic equation are from the products along the main diagonal. So that's very handy. It's also the case for diagonal matrices that getting the eigenvalues and the inverse are also very straightforward. So as we just said, for a diagonal matrix, the eigenvalues are sitting on the diagonal. Turns out the eigenvectors, you can immediately write down. They're 1, 0, 0, 0, 1, 0, 0, 0, and so forth. So they're all mutually orthogonal. In fact, diagonal matrix is symmetric, so you'd expect them to be orthogonal, as we'll show in the next section. So the eigenvectors are very simple. Not only that, the inverse is very simple as well. So as long as the determinant is not equal to 0, so A is invertible, the inverse of A is simply a diagonal matrix with the reciprocals of the eigenvalues on the diagonal. So diagonal matrix, eigenvalues on the diagonal, eigenvectors, super simple, mutually orthogonal, and the inverse, you just take the reciprocals of the main diagonal elements to get the diagonal inverse. In some cases, the question arises as to what are the eigenvalues and eigenvectors of a matrix to an integer power. So if we knew the eigenvalues and eigenvectors of a matrix A, what are the eigenvalues and eigenvectors of A to some integer power, say k? Well, we can derive the result very straightforwardly. So we have our original eigenproblem, A u is lambda u. Let's pre-multiply by A on both sides. So on the left we have A squared times u. On the right we have A times u, but from the eigenproblem that's just lambda times u. So then we have lambda squared times u. Do that again, pre-multiply by A on both sides. You have A cubed u on the left, and then the AU is lambda u, so that becomes lambda cubed times u. So you can quickly see the pattern developing here, and we can generalize this. A to any power k, the eigenvalues will be the kth power of the eigenvalues of A, whereas the eigenvectors of A to the power k are going to be the same as the eigenvectors of the original matrix A. So easy to remember, eigenvalues take the kth power, eigenvectors are the same. And again, we'll see this come up several times throughout the coming sections. Here's some remarks on eigenvalues and eigenvectors, some terminology. So in the process that we've used in the last couple of examples, the result that we get are what are called regular eigenvectors. They're eigenvectors that have come out of the regular procedure. There are situations, as we'll discuss, when we do not get a full complement of eigenvectors, and we'll talk about what happens in that case. But the eigenvectors we get through this process are regular eigenvectors. The set of all of the eigenvalues is called the spectrum of A. And the spectral radius is the largest by magnitude of the eigenvalues. It's also true that the eigenvalues of A and A transpose are the same. You can prove that. There's a proof in the book. And this next result is not terribly profound, but it provides a nice check on your eigenvalues. It turns out that the sum of the eigenvalues is the same as the sum of the diagonal elements of the original matrix. We call that the trace of A. So it's a very easy thing to check. Just add up the trace elements of A, so the diagonal elements of A, add up your eigenvalues, and they should match. And that gives you a little bit of confidence that you got the right eigenvalues. This next result is very important and is quite useful. So remember this one. So the determinant of A, it turns out, is the product of all of the eigenvalues of A. What that means, for example, is if one of your eigenvalues is 0, then the determinant of your matrix is also 0, and therefore it is singular. And that's actually an if and only if statement. An if and only if statement in mathematics is the strongest statement you can make. The way I like to think about it is you can read the statement forward and read the statement backward, and it is equally true. So in this case, what that means is if A is a singular matrix, so it has a 0 determinant, then at least one of the eigenvalues has to be 0. Likewise, if at least one of the eigenvalues is 0, then your matrix is singular. So you really have two equivalent mathematical statements. One thing that we're going to see in the next section is that the eigenvectors that correspond to distinct eigenvalues, so different eigenvalues, are always linearly independent. In some cases, they're also orthogonal, but they're always linearly independent. This is going to become helpful and useful in the coming sections. Cayley-Hamilton theorem. You may have heard of this theorem. It's a very simple sounding theorem, but it actually has quite a few very powerful implications. What it says is, if you have a matrix A, n by n matrix A, you get the characteristic polynomial, let's call it p sub n of lambda is equal to 0, so that's an nth degree polynomial. Turns out, if you take out the lambda and replace it with the original matrix A, it satisfies that equation. So essentially what we're saying is that A satisfies its own characteristic polynomial. Now, of course, you have to trade in a scalar 0 for a vector 0 on the right-hand side of the appropriate size, but it's a very powerful result and allows us to do a lot of interesting things with matrices. There is a proof of the Cayley-Hamilton theorem in the book. It's later in this chapter, and it uses the Schur decomposition. It's a really interesting application of the Schur decomposition. Now, in some cases where we have non-symmetric matrices with repeated eigenvalues, we're going to run into an issue. And the issue sometimes is that we're not going to get a full complement of eigenvectors using the regular procedure. So we're going to have fewer than capital N regular eigenvectors at times. So we say the matrix is defective. It has fewer than capital N regular eigenvectors, and we have to get additional generalized eigenvectors through a procedure that we'll see later in the chapter. I'm not going to do it now because it's actually not clear why we even need generalized eigenvectors. If I have fewer than capital N eigenvectors using the regular procedure, so what? What's the consequence of that? So when we get to a situation where that has implications that we need to deal with, then we'll address that at the time. So we really have, if you think about it, three cases when getting eigenvalues and eigenvectors. So you have your matrix A, you get your eigenvalues. If they're all distinct, then you get your eigenvectors, and you will get n, capital N, linearly independent eigenvectors, and everything's fine, regular eigenvectors. In the 4x4 example we did in the previous video, that was a situation where we had a non-symmetric matrix. It had repeated eigenvalues, but it so happened to give us capital N regular eigenvectors. The third possibility, which is the one that we're mentioning here and leaving to deal with later on, is where I have repeated eigenvalues again. I go through the regular procedure to get the eigenvectors, and I don't end up getting n. I get fewer than n. And that's when we need these generalized eigenvectors. So kind of think of it in those three possible categories of eigenproblems. Finally, just let me mention, there is what's called a QR decomposition. This is something we'll talk about later on in Chapter 2. There's a number of really powerful decompositions I've mentioned already. The QR decomposition is very powerful in its own right, but it also becomes the basis for numerical algorithms for determining the eigenvalues and eigenvectors of matrices. So, for example, if you ask MATLAB or Mathematica to get the eigenvalues and eigenvectors of a matrix, it's actually using an algorithm based on the QR decomposition. So we'll talk about the QR decomposition later in Chapter 2, and then we'll talk about the algorithm in Chapter 6 when we talk about numerical methods.